section 2.8, page 3. So we've talked about linearization. Now we're going to talk about differentials. So every variable has a differential. So x has a differential of dx. T's would be dt. The differential for z is dz. Here's how it breaks down. You should already be familiar with the Greek symbol delta, which means change or difference, right? So delta x is the change from the actual function to some point on the curve, and delta y is the change for the actual function. But if we use dx or dy notation, this is the differential notation, and this is talking about changes in the tangent line specifically. So what'll happen is you're going to have f of x, or you could use y, to represent your curve, right? This is the actual function, is the curve. But we have dx and dy, which are referring to my tangent line, and so my tangent line is this straight line over here that I've highlighted in pink. So when it comes to delta x, the change in the actual function, you're going to have some initial input x for a point on your curve and some other input value for a point q on the curve. So you go from 4 to 5, then you would be going from 4 to 4 plus 1. That's how you get the 5. So delta x is the change. Whoops, I shouldn't be circling that part yet. But delta x is the change from the first input to the next input, which are two different points on the curve. And that would be dx. But if you want to talk about the tangent line, we have x giving you some height p on the curve. And even when you scoot over delta x, if you're not going to the curve, but you're going to the tangent line, to the point r, the distance from the input is the same. So delta x and dx are the same, and that's going to be super important. But what's not the same is dy and delta y. So if dy is the change for the actual function, then my point x on the curve has a height of whatever this is. And when I come over to 5, or delta x further to the right, when I'm on my curve, I've got this. So from one height to the other, right, where the two heights are, I've got this distance from the actual curve of delta y. So it's not telling me what the output here is at point Q. It's just saying if you were to compare the height of Q and the height of P, this distance, this difference, is delta y, the actual curve. But remember, sometimes we're talking about the tangent line, and the tangent line usually is not on this curve at the second point, right? So what happens is if we were going to the second input, instead of landing on the curve, if we landed up here on the function, on the straight line, we want to know what is the difference from P to R, and this section is dy, because dy is referring to the tangent line. So to kind of state this in some other pieces and how it ties to the differential, we're using either y or f of x. They're the same thing, right? Whatever function notation you're using, then you're either going to say dy for the derivative, or you're going to say f prime of x. So it really just depends on which notation you started with. But regardless, when it comes to a differential, we're saying dy, this change from the tangent line, which is also the curve, and only the tangent line at some other point, it is exactly the slope of this tangent line, determined at point P. And if you multiply it by the change in the input, it's going to give you this difference right here, the length of that line. So that's what we're going to use for differentials. So if you wanted to find the output on the curve at Q, at X, where you scoot over dx pieces, it's super close to the actual function at whatever that first point is. And adding up this different piece, because remember, we're saying R and Q are going to be pretty close together. And so in the case of dy, though, we're going to use this formula. And we'll tie it back to the original on the next page. But for now, example 3 just asks us to find the differential. So we're not actually finding exactly what sine of 23x is, nor are we finding an approximation for this sine of 23x. We're just finding the formula that we're going to use later to find that. So I'm asked to find the differential. I know the differential is going to start off with dy for my answer. Then I need the derivative times dx. So my answer will end with dx. So the only piece I need to manually calculate is the derivative. So I know the derivative of the sine is the cosine, and it's of the same value. But because this value is not just x, I need to take the derivative of 23x to get 23, and then we tend to rewrite it out front. But now I have my slope times dx. Example 4 says, here is some function, you can call it y or f of x or both. You're given this polynomial looking function, and instead of just being asked to evaluate dy or to determine the differential, you're also asked to plug in some given values. So I do the same steps as above. I'm going to start off with dy equals. I need to determine the derivative of this function. So x cubed has a derivative, negative 2x squared has a derivative, constants have a derivative of 0, and then I'm just sticking dx on the end. And so I have my differential. That is what dy equals, but now I need to do the next piece. I need to evaluate it when x is 2 and dx is 0.2. So wherever x is, I'm going to put a 2. Wherever dx is, I'm going to put a 0.2. And for clarity, I decided to simplify inside of the parentheses because I was doing this without a calculator. Obviously, you could do it with a calculator, and you would want to type in, though, parentheses 3 times 2 squared minus 4 times 2, and then have your times 0.2. So you don't necessarily need all the parentheses, but I went ahead and just got the 4 to give me a 12, the 8 to subtract to a 4, and then I was able to solve this whole piece without a calculator. And remember, we have dy for our answer.